Great. Okay, dokie. Alrighty, chokey. Couple of things. We've got a quiz next Friday, so not this Friday, but next Friday. Last quiz, it's only on chapter 7, so that's pretty nice. How can I keep almost everything on one page? Let's try that. Okay, so crop this over here. Quiz number 4 is only on chapter 7, which I've got it scheduled ANOVAs for Tuesday. I'm a little bit tempted to move ANOVAs to tomorrow so that you'll have seen all the material this week, and then kind of cutting power calculations because I'm not going to test you on it anyways. So it's like a read when you have a chance or don't, see if I care type of a situation. So I might bump ANOVAs up to tomorrow, which might be nice. The quiz is still on Friday, but let's see here. Let's do it like this. I haven't decided 100%, which means I have to check to see if I'm allowed to cut power calculations. I think I am, but who knows? It's basically deciding your sample size. So quiz number 4 is going to be on assignment 14, assignment 15, and assignment 16, which is going to be on ANOVA, which I haven't posted yet because we haven't done it. Okay, assignment 15 is 7.2 and 7.3. So if you've tried it already, then the material we'll cover today will help you do the other half of the assignment. Okay. Whereas assignment 14 is section 7.1. Okay. So there will be another assignment 16 for ANOVA, but that's why I kind of want to try to squeeze it in this week, because then you'll have a whole week to work on that assignment as well and just kind of get it under control. Okay. All right. So, and then of course, quiz number 4 on November 25th, it looks like. It's just on chapter 7. Okay. The reason that I put the 2 sample means questions, so whether it's paired or today we're going to see 2 independent samples, I put them into one assignment so that you'd have a little bit of practice identifying which one which, right? Because that's part of the hard part as well on this quiz, but also on the final exam, is reading the question and then deciding, okay, what type of question do I have? Right, so as you're working through assignment 15, really pay attention to what type of question it is. Okay. What I did in this assignment 15 was, instead of incorporating the probability calculator into all of the questions, this answer because it doesn't have an answer, and also it's worth nothing. So don't worry about that. It was just to incorporate this. I couldn't figure out a way to have that not show up. But so that'll be question 1, and then you can just use it whenever you need to, right? I was worried that I would forget to include it if you needed it, or, so I don't want you to be thrown off by that. It'll just be question 1. Okay. I'm learning too. All right, so I think that makes more sense. There's also the formula sheet, which I just keep adding to, right? So we've seen all of this before, and we talked about one sample mean, right? That's 7.1. And then we went to paired data or matched pairs, which is just one sample mean, but of the differences, right? So nothing really changes. So that's 7.2. And then today we're going to use 2 sample means. Sometimes I like to emphasize it by saying 2 independent samples, just to emphasize that they're not paired anymore. So I did bring in this formula sheet into my notes here. And where did I put it? You gotta wonder. There we go. Okay. So here, 7.1, 7.2, 7.3. So today we're doing 7.3, which is called difference of 2 means. Oops, helps if I. Or sometimes I'll call it just 2 independent sample means. Two independent sample means. Just to emphasize that these 2 groups are independent of each other. When we have these 2 independent groups, then we're going to be talking about the difference of the 2 means. Whereas if we go back to that formula sheet, remember, for paired data, we talk about the mean difference, right? So the average of the differences. Whereas here, we're talking about the difference in the 2 averages. Ever so slight difference in interpretation, right? And so that's just something to stay on top of. And that's why I have it on the formula sheet, just to kind of guide you in the right direction. Because what this means is if I have 2 independent sample means, my interpretation has to be in terms of the difference of the 2 means. So here I'm going to say the interpretations, right? Whether it be your confidence interval, which of course we're going to build a confidence interval, or a hypothesis test, your conclusion, right? Both those interpretations have to be in terms of the difference of 2 means. Interpretations will be about the difference in the 2 means. So as before, I mean, we kind of ignore the sampling distribution because we don't have mu, we don't have sigma, so we use estimates in their place, right? To approximate x1 bar minus x2 bar, right? The difference in these 2 means. If we kind of take a step back and I say, okay, so the revenue of business 1, how does it compare to the revenue of business 2, right? The average revenue of these 2 businesses. What's your go-to action? Well, if I want to compare them, I would subtract one from the other. It doesn't matter how you subtract them, right? As long as you're consistent, right? And so, and that's exactly what we're going to do, right? In order to write or analyze about mu1, how it compares to mu2, we're going to use this as our estimate, x1 bar minus x2 bar. So kind of skimming through this here, the degrees of freedom, we are going to use this simplified version of the degrees of freedom, which is just the smaller sample size minus 1. So that means that we don't have to have the same sample size necessarily for two independent samples. Okay, and so how we denote that is just we write the minimum of n1 minus 1, or yeah, n1 minus 1 or n2 minus 1. There is a huge formula, but it involves like fractions above fractions above fractions and square roots, it's massive. So we're not going to do that. We're just going to take the smaller sample size minus 1. Right? But software would use that fancy degrees of freedom. It's no skin off their back. All right. Oops, wrong one. There. In terms of the conditions, nothing really changes, except now we have to talk about the conditions. We have to check the conditions for both samples, right? And we've seen that before with proportions. We had to check both samples, right? But the conditions were the same essentially, but now they really are the same. So what I want to do is paste this here. I want to keep it on this page. Okay. Just zoom in here. So the conditions, we can still use a t-distribution, and that's really nice, right? Now that we know how the t-distribution works, right? We know we need some degrees of freedom, and I mean, with a little bit more information, we know how to calculate the t, right? And then we're kind of off to the races. We know how to find p-values with the t-distribution, right? And so, so that's nice, right? We're going to stay with the t-distribution for a little bit longer, as long as we check the independence condition, which says that the data are independent within and between the two groups, right? So not just within each sample, they have to be independent, but also now we're saying, well, one of the conditions is that these two groups are independent of each other, right? How we ensure that is if the data came from independent random samples or a randomized experiment, then we can say, okay, I'm safe to assume that all the observations within the samples, but as well between the samples, are independent of each other, right? Same argument that we've been using all along, right? The normality condition, we can check the outliers. If our sample size is less than 30, it's more important. As soon as we hit over 30, then we can relax those conditions a little bit because the t-distribution can handle some outliers as long as the sample size is over 30. So I've got an example where we check those just as a reminder, but those are the same conditions, except now we check them for both samples. Yeah. We need the standard error. The standard error is going to be the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Again, we don't know sigma. That would be weird if we did, right? It means that we have population information that we've just thrown out, I guess. And so we use an estimate there instead, but that's okay. And then here's the note. The official formula for the degrees of freedom is quite complex and is generally computed using software. So instead, you may use the smaller of n1 minus 1 or n2 minus 1 for the degrees of freedom if the software isn't readily available. So here, this is what I have here, right? So the degrees of freedom is the smaller sample size minus 1. Let me just see. I think. I feel like I have it. Oh yeah. Technically, here's the degrees of freedom. Okay. Don't use that one. what is that? S1 squared over N1 plus S2 squared over N2 all squared all over 1 over N1 minus 1. It's all doable. It's all just algebra, right? So it's not that crazy, but do not use this if calculating by hand. I only show you this because this is what the probability calculator uses, right? When I show you that. So just so you're not kind of thrown off, but I want you to use just the smaller sample size -1. Okay. And I'll just highlight here that it has to be within and between the two groups. Okay. So if we're analyzing the difference in two independent sample means, really what we want to do inference about is mu1 minus mu2. What does that look like? So to analyze the difference in two independent sample means, can I say do inference? I can and I will. We do inference. Fine, I'll put like air quotes around the do. We do inference, which really is just confidence intervals or hypothesis testing. Conduct, I guess, would be about mu1 minus mu2. If I'm trying to learn about mu1 and mu2, but I only have sample information, a good replacement seems to be x1 bar minus x2 bar, right? So the point estimate here is x1 bar minus x2 bar. My best at what that difference is, right? Same as before. So then what we know we need is the standard error of the point estimate. So then the next step is the standard error of x1 minus x2. We were told that the standard error is sigma 1 squared over n1 plus sigma 2 squared over n2 all square rooted, right? But we're going to use our go-to move of replacing that sigma with s. Okay. So s1 squared over n1 plus s2 squared over n2. Notice that those sample standard deviations are squared. Okay. We're used to having s over root n as our standard error for x bar, right? And so now it looks way different until you kind of notice, and this is just for the connection. If you don't care, then that's okay. Notice that s over root n, which has been our standard error for x bar, right? If you rewrote it all under a square root, it would be s squared over n, which is arguably the same setup, right? There is such a thing. So remember, for proportions, we use the pooled proportion for hypothesis testing, where we can do a pooled standard deviation, but we will not. The reason for that is if we pool them, we're saying we assume that they're basically the same, and we don't need to do that anymore. And so we're just going to allow for two different standard deviations, and that's totally fine. What's nice is although this is a larger calculation, right? Once you have it, it's the same standard error that we use in the confidence interval as well as the hypothesis test. And so once you have it, you can reuse it, right? And so here, we use this standard error for both confidence intervals and hypothesis testing. So that's really nice. Same as before, I want to go through just the bare bones of what you need for a confidence interval and a hypothesis test, and then I want to do an example, and then I want to show you how you can use the probability calculator to solve these problems. I shouldn't have said that. We should have gone through all the work and then I'll show you. Well, it's still what we're going to do. Remembering the general setup of a confidence interval is the point estimate plus minus the critical value times the standard error of the point estimate. In this case, our point estimate is x1 bar minus x2 bar. And I'm going to put brackets around that just to emphasize that that's one value, one difference. Plus minus t star with degrees of freedom being the minimum of n1 minus 1 or n2 minus 1. And then the standard error of the point estimate is that square root of s1 squared over n1 plus s2 squared over n2. Okay. I want to emphasize again, I know I've said it before, but this means that the interpretation of the confidence interval has to be in terms of the difference in the means. Okay. So the interpretation of the confidence interval must be in terms of the difference in the means. But now that we have this, right, we know how to find a t star. As long as we're able to find the degrees of freedom, we can do that, right? I need to have x1 bar, x2 bar, s1, s2, n1, n2. All of that information is given in the question. So from there, it's just a plug it in and a plug and chug type of situation. So that's really all the new stuff that we need there. In terms of the hypothesis test, step one is to state the hypotheses. If I'm doing inference about how mu1 is different from mu2, right? We've seen this before. My null hypothesis that I prefer, and maybe I'll bump this down just a little bit more room, is that mu1 is equal to mu2. I just like to have mu1 equals to mu2. Technically though, what's our null hypothesis? Technically, it's mu1 minus mu2 equals 0. Those are equivalent statements, right? If mu1 is equal to mu2, then the difference of the two is 0, right? So whichever one you prefer is fine. Technically, for consistency, we should be using the second one, but I just think for clarity reasons, The first one is a little bit easier. And I think that's the one I have on the formula sheet. Let's see here. It is. So maybe I should add it on there. Anyways. Oh, don't look, it's the T. Well, you can look. So we'll get there. Okay. Some alternative hypotheses, mu1 is not equal to mu2, or mu1 is less than mu2, or mu1 is greater than mu2. We've seen this where we have to translate it to how does this inequality relate to 0, right? And so in this case, mu1 minus mu2 is not equal to 0. That one's the easiest one. If mu1 is less than mu2, then mu1 minus mu2 must also be less than 0. And then finally, if mu1 is greater than mu2, then mu1 minus mu2 must be greater than 0. So it's just another way of writing it. Step 2 is do the test. Which really means calculate the test statistic. We know that it's going to be a T because I told you so, okay? The general setup of the T is the point estimate minus the null hypothesized value, right? So in general, it's the point estimate minus the null value divided by the standard error of the point estimate. In this case, we said the point estimate for mu1 minus mu2 is going to be x1 bar minus x2 bar. The null value, and this, in this case, I am going to use this version here. The null value is that mu1 minus mu2 equals 0, right? We always assume the null hypothesis is true until we have proof otherwise. And so here, this is going to be mu1 minus mu2, which is always 0, right? Which equals 0 always. Okay. So that's why on the formula sheet, I don't even include it, right? It's just x1 bar minus x2 bar, technically minus 0 always, right? But that's why I just drop it. And we've seen that before, right? So then, over the standard error of the point estimate, which is the square root of S1 squared over N1 plus S2 squared over N2. Which is the standard error of the point estimate. Okay. Once we have this T, right, we can find the p-value, depends on the alternative hypothesis. Yeah. But step 3, find the p-value. First requires that we have the degrees of freedom. Degrees of freedom is the minimum of N1 minus 1 or N2 minus 1. Which, I don't know how many times I've written it already, but it's just the smaller sample size minus 1. Okay. Once you have your degrees of freedom, right, knowing that it's a t-distribution, right, we can find the p-value, so you can use that probability calculator. Use the probability calculator. To find the p-value. Depending on your alternative hypothesis, right, that's going to determine which area in the tails you want. So our three options, we have HA that mu1 is not equal to mu2, which is the same as mu1 minus mu2 is not equal to 0. If that's the case, my p-value, it's a two-sided p-value, not equal to, I need the area in both the tails. One thing to remember is that these distributions are always centered on the null hypothesized value, which is 0. So that might be helpful to remember. And that's always been the case, but it's one of those things I think I skim over until you're ready to hear it. If the alternative is that mu1 is less than mu2, or mu1 minus mu2 is less than 0, then my p-value must be the area in the lower tail. You want to be really careful, because if someone asks a question that contradicts what the data is saying, it's possible to get a huge t, a positive t, but then your p-value would be huge. So then you wouldn't reject the null hypothesis, right? So just follow through with what tail area you were supposed to do. That shouldn't happen, right? If we formulate our hypotheses carefully, then that won't happen. But I do remember, I don't know if I cut it or not, but there is one where it's basically asking you to prove that 30 is less than 20. Can't do that, right? In fact, there's a lot of evidence against that. Right? HA mu1 minus mu2 is greater than 0, puts us in the upper tail. Once we have that p-value, then we're ready for our conclusion, which is the same as always. We will do a conclusion. I am saying same as always, so that if you're kind of like, oh, I wish you would just say what the conclusion was. We spent a lot of time working through that, right? We have to compare the p-value to the alpha level. Then what's our conclusion in terms of H naught? And then what's the conclusion in terms of the question? And so this is my way of making you look it up from before. All right. Nothing to it but to do it. Here we go. Let's do an example. And this is actually an example that I appreciate, because it's probably the most common type of analysis that I do as a teacher. And honestly, in real life, most of your job, if you're analyzing things, will be a 2-sample t-test. It will be what we're doing here. How does group A compare, the average of group A compared to B, right? Drug trials, revenues, anything, as long as you can boil it down to comparing one group to the other for averages, it's a 2-sample t-test. And a lot of people just That's all they're doing all day. 2 sample t-tests, not all day, but half their days. Wait. So I have kind of I usually do a diamond example. It's the prices in 2 different carat diamonds, so a 0.99 carat diamond and a 1 carat diamond, and we analyze if there's a difference in the prices, which I think is pretty cute, but it's in the textbooks, so I know you'll go running for that. This one I think is a little bit more pertinent to us. Okay. Here's the situation. An instructor decided to run 2 slight variations of the same exam, which I have absolutely done, right? And so what's my main concern then? That there would be a significant difference in the grades between the two exams. Then I would need to change something, right? Even from one year to the next. As soon as I have different people writing different exams, it's a 2 independent samples t-test. So prior to passing out the exams, she shuffled the exams together to ensure each student received a random version. Summary statistics for how students performed on these 2 exams are shown here. We'll dissect that in a bit. Anticipating complaints from students who took version B, she would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult on average than version A, right? If that's the case, then we have a problem, right? Then I need to make some changes. Okay, so this is one of those kind of relatively rare instances where I'm just hoping that I get a big p-value, right? So I don't reject the null hypothesis. I want version A and version B to be basically the same, right? So we don't get any say in that, but here we go. So I've got the summary statistics here. I've got version A and version B. 30 people wrote version A, 27 wrote version B. The average of 79.4 is higher than 74.1, but our question is it significantly higher? That's what we're trying to answer. We have slightly different standard deviations, 14 and 20, right? And then we have the minimum and the maximum, which we are going to use to identify if there's any outliers, right? Any values that we need to be concerned about for that normality condition. If you were reading this question, say it's part of the quiz, right? What are some telltale signs that this is a 2 independent samples mean question? Ugh. Grammar. First off, I have sample information for 2 samples, right? Which boils it down to, okay, it's either a paired samples t-test or 2 independent samples, right? If it was paired, right, I would also need the mean of the differences and the standard deviation of the differences. I don't have that here, so that's kind of nudging me towards 2 independent samples. What really seals the deal for me is that the sample sizes are different. They can be the same in 2 independent samples, and they often are, but if they're different, that tells me that this data can't be paired, right? 30, I can't pair 30 with 27. That doesn't make sense, right? And so you're gonna need those kind of check-in points, right? And of course, reading the question and say, okay, well, it looks like a group of students wrote test A and a different group of students wrote test B, right? So all the while, I'm just convincing myself that this is 2 independent samples, right? So I just want to write here that since N1 does not equal N2, this can't be paired data. It can't be a paired data question, right? And I'll follow it up here. Would also need X bar of the differences and S of the differences. Right, which we don't have. So now I can kind of breathe easy. Why do I say that? Because once I've decided, especially for quiz 4, where we're restricted to 3 regions here. Once I've decided that I have a 2 sample means question, right? 2 independent samples, then I've only got eyes for this section, right? There's nowhere else that I need to be looking. Everything that I need is here. Okay? So that's why I encourage you to take a little bit of time and just make sure that you've got the right question type, and then you can kind of zoom in and go for it. Especially on the final exam, right? Where all of these types of questions are going to be in one heap, and you need to figure out which type it is. Okay. Let's start by checking the conditions. Although in reality, you would do the analysis anyways, right? You check the conditions, even if they don't check out, you would say, okay, well, how about we proceed with caution, right? When you're reporting to your client, you would say, there were some normality issues, but here are the results, so be careful. And then that's it. But for us, right, we're here to learn the nitty gritty. First one is the independence condition. It does say that she shuffled the exams together to ensure each student received a random version, right? And so since each student received a random version, we can assume that the students within each version and between the versions are independent of each other. So, oops. Since each student received a random version, how do you spell received? I before E, except after C. I'll just copy how they spelled it. Sometimes even when I'm writing by hand, I wait for the little red underline. Doesn't work. So since each student received a random version, I should say up the test, we can assume the students, we can assume the students within each version and between the versions are independent of each other. It's really important that you touch on the within and the between, right? And check off both of the samples as well as how they relate to each other. The second condition is the normality condition. Our cutoff is 30, right? If the sample size is less than 30, then we need to put in a little bit of work to make sure that there are no extreme outliers, right? And so one way that we could do that is to make a histogram. I don't have a histogram, that's okay. We are given the minimum and the maximums. So what we can do, right, and those cap our data. There are no values beyond those points, obviously. And so if I check that the minimum and the maximum are not outliers, right, then I can assume that there are no outliers in general, right? So because 30 is on the cusp, I'm just going to go ahead and do it mostly for practice, right? Better safe than sorry. So But 27, right, using the 30 cutoff, we would check for outliers. If both of these sample sizes were over 30, right, then we could just say the sample sizes are large enough, so we assume the normality condition is satisfied, right? So as soon as you hit that threshold, you're off to the races. You don't need to worry about it too much. Okay. So the normality condition, since N1 equals 30 and N2 equals 27, and maybe I should use A and B instead of the generic. Hey, I did it here too. I can't be tamed. How about NA and NB? Do it here too. I'll probably slip up again. Yeah. So since these are less than or equal to 30, we will check for, so since NA is 30 and NB is 27, the sample sizes are less than or equal to 30. So we will check for outliers in both samples. How am I going to do that? What I'm going to do is I'm going to grab this so I don't have to scroll around here. Okay. So for sample A, I'm going to focus on the minimum and the maximum, right? Everything else is closer. So what I have is, I'm just going to visualize it with a number line. So the minimum is 45 and the maximum is 100. When we're talking about grades, it makes sense that both the maximums are 100, right? Someone got 100% on both of the versions, right? Well, that's impossible if you only wrote one version, but I think you know what I mean. I'm going to put down the mean of 79.4 because that's really what I want to know. How far from the mean, how many standard deviations from the mean are the minimum and the maximum? So I'm just going to jot down here. I don't spend a ton of time trying to figure out where it's going to go on this number line. It's just to visualize it. So what I need to do is I need to figure out how many standard deviations 45 is from 79.4. So 45 minus 79.4 divided by the standard deviation, which is how we calculate the spread. And I have it here, negative 2.46, which is quite far, right? But it's still within reason. We're pretty flexible. I encourage you to use maybe 3 as a cutoff, right? 2.5 is good, right? But 3, then we draw the line and we say, okay, there's some outliers here. Can't go ahead. For how far is 100 from 79.4 in terms of the standard error? It's going to be 1.47 standard deviations away from the mean, which is totally within reason. And so here, this is the one that I'm concerned about, but this is less than plus minus 3. Should do the absolute value of 3, but I think you understand. I mean the magnitude, right? So it is not considered an outlier. Okay. If we do the same thing for sample B, I'll try to keep it on the same page here. The minimum on sample B is, or version B, I guess, is 32. The maximum is 100. The mean was 74.1. You'll be faster than me talking about it, right? If you just kind of figure it out and just do it, you'll be way faster than me. 32 minus 74.1 divided by the standard deviation is now 20. And I get negative 2.105. And then if I do 100 minus 74.1 divided by 20, 1.295. Looks to me like everything is within 3 standard deviations from the mean. So I'm not too concerned about this, right? And so neither of the samples have any extreme outliers, so we can assume normality. So I'll write that down here. Neither of the samples have any extreme outliers. So we can assume normality. Maybe I should change it to the dark blue because it's actually part of the blurb. There. So now we've checked the conditions. We're good to go. So now we're actually going to do this hypothesis test, right? Because if we want to evaluate whether the difference in the groups is provides convincing evidence that version B was more difficult on average than version A, that's a hypothesis test, right? And so as soon as we need to gather evidence, or was there evidence that this happened, then we're doing a hypothesis test. So step 1, state the hypotheses. I want to show my null hypothesis is that mu A is equal to mu B. The mean is the mean grade, right? And so if the mean of version B was lower, that means it's harder. And so what does that, how does that translate here? Oh, H A then is mu A is greater than mu B. I'll not use green yet. Or if you prefer, mu A minus mu B, I always forget, is equal to 0. And if mu B is less than mu A, then mu A minus mu B is greater than 0. Use those interchangeably. Right. Definitely be able to read both of them and say that they're the same. Okay. Step 2, do the test. Which is T is X1, and maybe I'll grab it from the formula sheet so you can see it. See it in action here. So T in our case, sure, I'll put it below. T in our case is going to be XA bar minus XB bar. And like I said before as well, it doesn't matter which one you treat as group 1 and group 2 as long as you're consistent. And if I grab this information here, because I'll need it. Wait. Hello? Doesn't want to paste. Okay. I don't know, I guess it did it. Weird. S1 squared over N1 plus S2 squared over N2, then square root it. Plugging in all this information, all right, where it's supposed to go. I have X1, and I always treat them in order, right? So the first one is group 1, the second one is group 2. Otherwise, I get way too confused, right? And so 79.4 minus 74.1 divided by the square root of 14 squared over N1, which is 30, plus 20 squared over 27. And square root it. Wonder if it saved it. I did it in this, it did. Okay. So here, first I found the inside the square root is 21 point something. And then once I take the square root of that, I get 4.62 is my standard error. And then when I calculate my t, it becomes 1.1471 basically. So instead of typing that all out again, how about I just copy it in here? Crop it up. Okay. So this means that t is 1.1, oops, there I go. 1471 if I, or maybe I'll write out the whole thing. 0.85436, right? And that's from here. Let's go to 4 decimal places. One thing that's worth, I feel like I've mentioned it before, but in MOM, the tool that we use to do our assignments and the quizzes, the default is 4 decimal places. So if you go to 4 decimal places, you'll always be safe. 1.1471, going to 4 decimal places. Okay, so now I have my t. As the teacher in this scenario, I'm relieved. Why? Because that's not very extreme. I get the feeling that I'm not going to be rejecting the null hypothesis, which in this case is a good thing, right? Because it means that the 2 versions are not significantly different, right? But let's get the p-value just to confirm. Oops. Step 3, find the p-value. The degrees of freedom is the minimum of n. I will use the generic one, n1 minus 1 and n2 minus 1, which is the minimum of 30 minus 1 or 27 minus 1, which is the minimum of 29 or 26. Well, the minimum of 29 or 26 is 26. If you're not used to that minimum notation, it's worth getting used to. It's kind of a nice, clean way of writing the degrees of freedom. Okay, so I want the area in the upper tail, right? Because my alternative hypothesis is that mu A is greater than mu B, or mu A minus mu B is greater than 0, right? And so let's just go to that probability calculator. Skip straight to it here. And how? Okay. First thing I need to change is I need to change it from the normal distribution, which is the Z distribution, to the student T distribution, which means I need to give it some degrees of freedom. We just decided it was 26. Uh-oh. It was giving me a hard time earlier today, but okay, we'll see how it goes. So then we said we want the area in the upper tail, which I will make a note of once we've done this. So I'm going to change it to the area in the upper tail because it's that one side of the and 0 alternative. And then here's where I put my calculated T, which was 1.1471. I find my p-value is 0.1309. So I'm gonna grab this, oops, screenshot. Okay. So here, notice that, right, since HA is that mu A minus mu B is greater than 0, because it's centered on 0, right? So then I find that that one's easier to work with. The p-value then is going to be 0.1309. And the degrees of freedom that we found here is what goes here. And then, of course, it has to be the student distribution, the student's T distribution. Okay. Now, we're ready for our conclusion. Same way as always, right? We start by comparing the p-value to the alpha level. There was no alpha level given, so we're going to use 0.05. So I'm going to say since the one-sided p-value of 0.1309 is not less than the assumed alpha level of 0.05, is not less than the assumed alpha level of 0.05, we do not have enough evidence to reject H0. We do not have enough evidence to reject H0. In terms of the question, what does that mean? It means that there is not enough evidence to say that there was a significant difference, or that rather that version B was significantly harder than version A, right? Therefore, there is not enough evidence to say version B was more difficult on average than version B, or version A was more difficult on average than version A. Just as a reminder, right? This is in 3 parts, comparing the alpha or the p-value to the alpha level. then your conclusion in terms of H naught. And then finally, the one people love to forget about, the actual conclusion that you were paid to do if this was a work situation. Right. I want to show you some other functionality in this probability calculator. So we've been working in the distribution tab. I cut it off here. But if we go to the statistics tab, I would just want to show you some of the options. We've been there before and I showed you, okay, here's how you could do a chi-squared test using this thing. Okay. But in the statistics tab, if you go to the drop down, and that's where we had the chi-squared test at the bottom, but I'm just going to screenshot this so we can talk about this list, because there are some ignorable options that we absolutely do not use anymore. Makes you wonder why they would even be there. No clue. So the options here, well, first let's talk about in general. These are all options for doing hypothesis tests. And then as soon as we're talking about an estimate, these are confidence intervals. It's a good place to start. We don't do z-tests for a mean anymore because it's not, the 1900s. So there was benefit to having, okay, well, if we just make some more assumptions, we can just assume that it's a fixed distribution, right? Remember, the problem with the t-distribution is that it moves depending on your sample size, your degrees of freedom, right? So you can see how they would be kind of into not having to deal with that. But as soon as there's a z-test for a mean, you're not going to do that, right? The options that you can use is a t-test of a mean, which is a one sample test, which is also where you would do your paired data because it is just the one sample. The difference of the means, that's what we were doing today or are doing today. You've already seen a z-test for a proportion and a difference of proportions. Those you're allowed to use. Again, as soon as you see a z for a mean, you do not go there. You can use a t for a mean or a difference of means. You can use a z for proportions, which we've already done in chapter 6. Okay. So what I want to show you, or maybe here. We can use the statistics tab, and I'll have a screenshot of it. So we can use the statistics tab, and maybe I'll just kind of highlight that it's a tab here. In the probability calculator. Okay. So what I want to do is I want to show you how you would do this t-test, the difference of means. In the statistics tab. It's all grayed out. It doesn't even give us another option than mu1 minus mu2 being 0. That's the only option. We are gonna change the alternative hypothesis to be greater than, because that's what we wanted. Ignore the pooled, because we're not gonna do that for this. For proportions we did. The mean of sample 1, and this is where it was giving me grief, was what, 79.4. Then I have to go back and delete that question mark. The standard deviation was 14. N was 30. the mean was 74.1 for group 2. Standard deviation was 20 and N was 27. Once I kind of tap it and commit to that, it produces all this output. So this is what I want to take a screenshot of. Oh, wrong window. Let's see if I can. Make it bigger. There we go. Okay. So here, this is what I mean by the statistics tab. Oh, draw over it. There. We said we were going to do a t-test for the difference of the means. And then notice the standard error that it calculates is the same as what we found, right? But the degrees of freedom are way different. This is using that crazy formula. So our p-values will not be the same. Okay? On the quiz and on the final exam, I'll accept either one, right? And so mostly because notice how the p-value of 0.1286 is not that different from 0.1309, right? So then the t that they calculated is the same as ours, right? And then there's the p-value. So kind of fun. Just as a heads up though, right? If you're checking, oh, my p-value is different. It will be different because they are able to use more degrees of freedom. We were just playing it safe, right? So here, warning, it uses the fancy degrees of freedom calculation, which we're not going to do. So the p-value changes slightly. You can still use it to check your t calculation though, right? Because, I mean, once you've entered all the information, then the t's should end up being the same. Okay? This, I guess, feels like cheating. It's not, right? Because our job is just to be able to read the output. Yes, I would love for you guys to be calculator whizzes, but you don't have to be. We've put in the work. You guys have done enough calculations. All right. I also want to show you how to do the confidence interval. And then you could do it by hand. You can check it by hand. How would we do a confidence interval for this difference of means? It's the t estimate difference of means. What's really pretty fun is that it kept all the numbers from before. Magic. So I forgot that it did that actually. Nice surprise for me too. So we can also calculate, and I think I'm gonna have to put it on a new page here. Maybe, let's see here. Okay, so now I'm doing the confidence interval is what that's saying. I didn't change it. I'll just do a 95% confidence interval. It kept all this information and it gives me the upper limit and the lower limit. Notice again that it uses this different degrees of freedom. So if you're doing it by hand, we would have fewer degrees of freedom. So our interval would be wider. So just notice that this would be different than by hand. But we can still interpret this interval, right? I have an interval from -4 to 14.6 pretty well. So we are 95% confident the interval from -4 to 14.6 captures the difference in mean grades from version A and version B. Captures the difference in mean grades on version A and B. A confidence interval by hand will be slightly wider with fewer degrees of freedom. Okay. But you can still use it. It should be in the realm of -5 to 15 or something like that, right? So it's not going to make a huge difference, but it will be slightly different, but still in the realm. So definitely worthwhile getting to know kind of this probability calculator. What can I do here? And that's all I have to say. If you have any questions, let me know. Otherwise, I will see you tomorrow. Wow. Stop this recording here.